Okay, in this video, we're actually going to do what's called proving identities. Uh, Proving an identity means to show that both sides of the equation are the same. So let me word it like this. On this first problem, it says the tangent of theta divided by the secant of theta is equal to the sine of theta. So that's an identity. That's a true statement. We could actually, that list of identities that we had on our last worksheet or on our last section, we could add this to our list. We're not going to, but we could add this to our list. However, we're going to go through the process of proof. Well, why is this true? Is it true? Why is it true? So we're going to go through the process, and the way that we're going to go through it, honestly, is the exact same thing we did on the last lesson. These are going to be super. If you understood those, these are going to be super similar to those because what we're going to do in order to prove that these are the same. Look, it says simplify one side using the basic trig identities of the equation until it is the same as the other side. Ideally, pick the side that is more complicated. So like on this first problem, tangent over secant, what we're going to do, we want to make sure, or we're going to show that that's equal to sine. How are we going to do that? We're going to take the complicated side, we're going to clean it up just like we did last section. But what's nice about it is now pretty much we know what the answer is. We want to take the complicated side, which is tangent over secant, and we want to somehow prove that that's equal to this. So let's take tangent over secant and do the exact same thing we did last lesson. Tangent I know is the same thing as sine over cosine, and you can look at your list of identities. Secant is the same thing as 1 over cosine. If you were to flip and multiply, to divide these fractions, you flip and multiply. That's sine over cosine times cosine over 1. The cosines cancel and leaves you with sine. So therefore, since this is sine on the right side, it's equal to sine, then check. You've proven that those two identities are the same. That's all you have to do. The second one, 1 plus secant squared times sine squared. We want to prove that that is secant squared. Well, how are we going to do that? Let me erase that. Well, first off, let's pick our complicated side. 1 plus secant squared times the sine squared. That looks so much sloppier than the other side. And let's clean it up. I know that secant I can turn into cosine stuff. So secant squared is 1 over cosine squared. And sine squared I'm going to leave. To multiply those two together, you multiply tops and bottoms, and that gives me 1 plus sine squared over cosine squared. I know that sine over cosine is tangent, so that'd be 1 plus tangent. And since it's sine squared over cosine squared, that'd be tangent squared. And if you don't remember, let's scroll up. I've actually got all my identities up here from the last lesson right here. Tan squared plus 1 is equal to secant squared. Can't we use that now? So tan squared plus 1 is equal to secant squared. So check, check, all that stuff does equal secant squared. Next problem, pick the ugliest side, which would be cotangent over secant plus sine. Let's change all the cotangents and secants to sines and cosines. I know that cotangent, by the quotient identity, the cotangent is equal to the cosine over the sine. Over, I know that secant is equal to 1 over cosine. I still have plus sine. To divide these two fractions, I'm going to flip and multiply. So I'm going to do times cosine over 1. So that would equal cosine squared over sine. Now I got to do plus sine. Obvious thing to do now is to actually add these two together. So I need a common denominator. So in order to find that common denominator, what I'm going to do, I'm going to multiply top and bottom by sine. So I've got a sine on bottom and I have a sine squared now on top. Combine the two and I have cosine squared plus sine squared. That sounds familiar, over sine. We know that from your most basic Pythagorean identity that cosine squared plus sine squared on top is equal to 1. So we can replace cosine squared plus sine squared with 1. And finally, 1 over sine. If you look back to your reciprocal identities, 1 over sine is the same thing as cosecant. So we have proven that those are equal. Number 4, take the most complicated side, which is obviously this side, and we want to somehow turn that into sine to prove that they're equal. I do want to point something else out. Let me go to Desmos here and show you something. Okay, I pulled up Desmos, and look what I've done here. I've typed in cosecant x, and I used x. Desmos wants x instead of thetas. Cosecant x minus cotangent x times cosine of x, and look what I get when I graph that. That looks like a very familiar graph, and if I were to graph just plain sine x, you see that those are the exact same graphs. So obviously they are the same, and that's a way that you can actually check, well, are they equal? If they have the exact same graphs, then obviously they're equal to each other. So now, how do I prove without a graph? How do I prove that those two things actually lie right on top of each other graphically? And that's what I'm doing here. I'm going to take the most complicated side, and obviously 1 over cosecant I can replace with 1 over sine. Minus cotangent is cosine over sine. And you see a lot of repetition here, and cosine there, so you have times cosine over 1. So you now have 1 over sine minus cosine squared over sine. And those already have a common denominator, so you now have 1 minus cosine squared over sine. 1 minus cosine squared on top. Again, you see the square. I know that, let me do cosine first because that's the way they write it. I know that cosine squared plus sine squared is equal to 1. So if I were to move cosine squared over, I get that sine squared is equal to 1 minus cosine squared. So I can replace 1 minus cosine squared then with sine squared. So I have 2 sines on top. It's kind of like x squared over x. I have 2 sines on top, 1 sine on bottom. The 1 on bottom cancels with 1 on top, and I'm left with sine. So you have sine of theta, you have sine of theta. Those two have, they are equal. Number 5, again, it's obvious which one's the more complicated side. So I'm going to take this side and try to clean it up. On top, you have cosecant, which is 1 over sine, times cosine. And you can put cosine over 1 if you want to, because you're probably going to have to multiply them. On bottom, you have tangent, which is sine over cosine, plus cotangent, which is cosine over sine. On top, I'm going to multiply those, and it gives me cosine over sine, which I don't know, that's actually cotangent there. So I don't know if there's something you can do with that to work this a little bit differently. There's several options here. On bottom, now I need a common denominator. So what I'm going to do, I'm going to multiply top and bottom by sine here. So it gives me sine squared on top. We'll multiply top and bottom over here by cosine. So now I have my common denominator. So on top, I have sine squared plus cosine squared. On bottom, I have sine times cosine. I notice that cosine squared plus sine squared on top right here, that's that most basic fundamental identity. So I can replace sine squared plus cosine squared with 1. So now I have cosine over sine divided by 1 over sine times cosine. To divide two fractions, you flip the second one and you multiply. So I now have cosine over sine times sine times cosine over 1. The sines cancel and leaves me with cosine squared, and I believe that's what we are looking to make it equal. Number 6. Left side is most complicated. So let's try to make it equal 1. Secant is 1 over cosine. Cosine is itself. Minus tangent is sine over cosine. Over cotangent is cosine over sine. I have what's called a complex fraction in both of these. You have um, both of them are a fraction divided by a fraction, or a fraction within a fraction. So what we're going to do on both of these are flip and multiply. So to divide by cosine over 1, I'm going to multiply by 1 over cosine. To divide by cosine over sine, I'm going to multiply by sine over cosine. Flip and multiply. So I have 1 over cosine squared minus sine squared over cosine squared. And that worked out great because you actually already have common denominators, so you can subtract these. So that gives me 1 minus sine squared over cosine squared. And I can actually, let's see, I thought I had it written down somewhere else. But since I know again, it goes back to cosine squared plus sine squared equals 1. You use it a ton. If you were to move the sine squared over, you have 1 minus sine squared is equal to cosine squared. So right here where you have 1 minus sine squared here, you can now replace with cosine squared. And that turns into cosine squared divided by cosine squared. They cancel each other out, and that's equal to 1, which is what we were looking for. Anything divided by itself is equal to 1. Now the next one, we've actually already done this. We did this one last section because what we did, we knew that sine squared plus cosine squared was equal to 1. We took out cosine squared. You can actually do it either way. I think it's going to be easier to take this and to try to turn it into that, because all you have to do is take out cosine squared and replace it with 1 minus sine squared. So now you have 1 minus sine squared, which is 1 minus 2 sine squareds, which is equal to that. Next one, let's simplify the left side. Secant squared, that'd be 1 over cosine squared, times cotangent squared, that'd be cotangent is cosine over sine, so that'd be cosine squared over sine squared. And you still have minus 1 out there. Cosine squares cancel and leaves me with 1 over sine squared minus 1. I know 1 over sine is cosecant, so 1 over sine squared would be cosecant squared minus 1. And that is one of your, let's scroll back up and just show you. That is one of your Pythagorean identities. Cosecant squared minus 1. Cosecant squared minus 1 is right here. If you take and you move the 1 over, you have cosecant squared minus 1 will equal cotangent squared. So now scroll back down. Cosecant squared minus 1, you can just replace with, again, cotangent squared. And so it checks out. Those two are equal. Next one. I'm probably going to start on the right side over here. And let's see, what can we do with that? Cosecant squared minus 1, I believe we just used that one. That's one method of doing it. If you want to go ahead and replace that with cotangent squared, I think that's going to be a little bit cleaner, because if not, you're going to have to do some common denominator stuff. So let's start there. Let's take our cosecant squared, and in cosecant squared minus 1, we're going to replace that with cotangent squared. So now we have on top, cosecant is 1 over sine squared. Well, actually, cosecant is 1 over sine. Cosecant squared will be 1 over sine squared. Cotangent squared will be cosine squared over sine squared, and that made things so much easier, because when you flip and multiply, the sine squareds will cancel, and we'll leave you with 1 over cosine squared. And we know that 1 over cosine is secant, so 1 over cosine squared will be secant squared, which is what we're trying to turn it into, secant squared. Next one, let's try to clean up probably the right side. Again, you can do either one. There's not a whole lot you can do on the left side, so probably the right side. Cosecant, we're going to replace with 1 over sine. And inside we have cosine plus sine, distributive property. And we pretty much have the answer. 1 over sine times cosine would be cosine over sine, plus 1 over sine times sine over 1. The sines will cancel and leaves you with 1. And I know that cosine over sine is equal to cotangent, so I have cotangent plus 1, which is what I was looking for. And the last two. We have the more complicated side on the left. Not a lot you can do on the right side there. So I have cosine plus sine times tangent would be sine over cosine. So I now have cosine plus sine times sine would be sine squared over cosine. I need a common denominator. So I'm going to multiply top and bottom over here by cosine. So I have a cosine on bottom now, and I have a cosine squared on top now. So we can now combine these as cosine squared plus sine squared over cosine. I know that cosine squared plus sine squared is the most fundamental Pythagorean identity. That is 1 over cosine, and 1 over cosine is equal to secant. And the last one. And you have your options here. I'm going to start with the left side. The right side, you could factor it. That'd be difference of squares. That's about all you could do there. Or you could do 1 over sine squared minus 1 over cosine squared. You might come up with the left side, but I'm going to just start on the left side. On top, I have cotangent would be cosine over sine minus tangent is sine over cosine divided by sine times cosine. I'm going to do some on top, do some common denominators. I'm going to multiply top and bottom here by cosine. So I've got 2 on top now. Multiply top and bottom here by sine. So the same thing, I have 2 on top now. So I have on top cosine squared minus sine squared. And I have my common denominator, which was sine cosine, divided by sine cosine over 1. When you flip and multiply, it actually is not gonna, what you think is gonna happen does not, because when you flip and multiply, you're actually gonna multiply by sine, cosine on bottom, and they don't cancel like they normally do. So what you've got now is cosine squared minus sine squared on top, and you got to multiply these two together, which just multiply sine times sine. You don't have to FOIL or anything like that. That'd be sine squared times cosine squared. Okay, and the next step is a little bit tricky, and it'd be hard to see this if you've not worked one of these before. Let me come over here and let me remind you of something that you've done several times, but you just need reminding of it. 2x plus 4 divided by 2 can be split into 2x divided by 2 plus 4 divided by 2. And a lot of these tricks, the more that you see these, the more you're going to get used to them. This is called the distributive property. The reason we can use it is because we have a binomial on top. A binomial means there's 2 terms, but we only have a monomial on bottom. And you might be saying, but you don't have a monomial on bottom here. Actually, yes, you do, because there are no plus or minus signs. You could actually split this. And that's what we're going to do. Let me erase and make some room, and I'll just continue with my blue marker here. So I'm going to divide both of these. Cosine squared divided by sine squared cosine squared minus sine squared divided by sine squared cosine squared. And look what happens. Cosine squareds will cancel here and leaves you with 1 over sine squared minus sine squareds cancel here and leaves you with 1 over cosine squared. I know that 1 over cosine or 1 over sine is cosecant, so that'd be cosecant squared minus 1 over cosine will be secant. So it leaves you with cosecant squared minus secant squared, which is what you're looking to turn that into. One last trick that I do want to show you that sometimes comes in handy. Sometimes in a problem, wish to add some more room here. Sometimes in a problem, you might have something like 1 over 1 minus sine on bottom. And what you can actually do is sometimes you might have to, the same way that, let me compare it to something that you've done. 1 over root 3 plus 2. The same way that you can get a radical off the bottom, the process was called rationalizing. The way that we rationalize this is we multiplied top and bottom by the conjugate. Well, you can do the same thing here, because if you remember what I told you a while ago, that whole stuff about factoring these things, if you were to multiply top and bottom here by the conjugate of the bottom, 1 plus sine theta and 1 plus sine theta. Look what happens, and this is just another trick that sometimes you need to use. 1 times that, on top you're going to have 1 plus sine theta. On bottom, those are again, they're conjugates. The same way here, you can do root 3 times root 3 and positive 2 times negative 2. You do 1 times 1 is 1. Negative sine times positive sine would be a negative sine squared. And we know that from cosine squared plus sine squared equals 1, that anytime you have 1 minus sine squared, look what you can turn it into. 1 minus sine squared is equal to cosine squared. So anytime that you have like a binomial on bottom, sometimes in order to solve one of these, you might have to multiply by the conjugate to turn it into something that might be able to cancel down the road.